So can you see it?
Yes, yeah. All right, so our first speaker is Matteo Morittu from the University of Oviedo, and he will be talking about type 2 orientifold flux vacua in 3 dimensions. Matteo, please go ahead.
So thank you very much, George, and thank you all for attending the seminar. So today I will try to review some recent progress in constructing anti-de Sitter vacua from type 2 orientifold, in particular adopting the perspective of supergravity. The talk is based on some recent works done in collaboration with Álvaro Arbolella, Gabriele Casagrande, Adolfo Guarino, and Giuseppe Sudano, who might be here in the audience. So two main challenges in string compactifications, as we all know, are the following. First of all, we would like to stabilize the moduli, and then in a vacuum, we would like to achieve a parametrically controlled hierarchy of scales between an external space, typically anti-de Sitter, and the internal space of the extra dimensions predicted by string theory. This property is known as scale separation. We also know that for the majority of anti-de Sitter vacua of string theory, gravity is not actually genuinely lower dimensional, in the sense that these vacua are not scale separated. However, there are few constructions of supersymmetric anti-de Sitter 4 vacua from flux compactifications which admit the property of being scale separated. They are the so-called KKLT model and the DGKT construction. These constructions are actually still under some debate, and in order to avoid the intricacies, the possible intricacies that might be involved when considering these constructions, we decided to focus or to search for similar but simpler setups. And we will then focus on three-dimensional theories of gravity coupled to matter in the presence of supersymmetry. While doing so, we will always keep an eye at the swampland program and its expectations. For instance, we know that scale-separated supersymmetric anti-de Sitter vacua are predicted to be in the swampland. This is the so-called strong anti-de Sitter distance conjecture. And we also know that non-supersymmetric anti-de Sitter vacua are conjectured to be unstable. We will try, this is our goal, to initiate a systematic study of the landscape of vacua in 3 dimensions. And when trying to do so, we will also keep in mind, we always add back in our mind, actually, some further expectations. For instance, the fact that achieving scale separation in 3 dimensions from type 2b is quite hard, and that the conformal dimensions of the would-be dual TFT2 operators when considering type 2b anti-de Sitter 3 configuration are rational valued and not integer valued as we would like. Then, equipped with these expectations, let me actually go into business and present you some, present you half-maximal supergravities in 3D. We'll do this adopting 2 different approaches. So following the original Scherken-Schwarz construction, we can reduce type 2 supergravity on a 7-dimensional, on a locally 7-dimensional group manifold down to 3 space-time dimensions. A group manifold comes along with its own parameters, the metric fluxes, and the metric fluxes specify the geometry. They are the structure constants of the Lie algebra that the isometry generators on the group manifold satisfy. Topologically, non-trivial cycles on the internal space can support background constant fluxes coming from the Neveu-Schwarz 2-form gauge potential and from the Ramond-Ramond P-form gauge potential. They are the H3 flux and the P-form FP fluxes. They can be expanded, as I show in the slide, on a basis of 1 forms, the eta basis, which is constructed in terms of the coordinates ym of our group manifold. A compactification also includes other objects, Kaluza-Klein monopoles, Neveu-Schwarz branes, DP branes, and OP planes. Specifically, we'll consider a compactification involving a single type space-time filling OP planes and DP branes. And this is why, so to say, the metric fluxes, the omega fluxes, satisfy the Jacobi identity that you see here. They are telling us there are no Kaluza-Klein monopoles in our compactification scheme. The H3 flux satisfy a Bianchi identity, telling us there are no NS5 branes in our compactification. And then the P-form fluxes satisfy the corresponding Bianchi identities, and the only non-vanishing net current, JOP-DP, is the one associated with a single type of OP-DP sources we are introducing in our compactification. Extended objects, as we know, break supersymmetry because they break some translational symmetries, and then the supercharges which close into the broken momentum generators in the superalgebra. Introducing a single type of OP-DP sources brings us to having a half-maximal amount of supersymmetry in 3 dimensions. That's why, upon compactification of type 2 supergravity on our group manifold in the presence of a single type of OP-DP sources, we end up having a half-maximal and equalate supergravity in 3D. And half-maximal supergravities in 3 dimensions have their own descriptions in terms of the so-called embedding tensor formalism. The field content of half-maximal supergravity consists of the gravity multiplet made by the spacetime metric and 8 gravitini, and then we consider the presence of n equal 8, of 8 matter multiplet, each one composed by 8 real scalar fields and 8 spin 1/2 fermions. The bosonic Lagrangian of the model is reported in the top part of the slide and can be written in terms of a matrix M, and it also includes a scalar potential V. We are considering gauge supergravity. From the higher dimensional perspective, fluxes are turned on, both metric fluxes and gauge flux. The matrix M is constructed in terms of a coset representative, nu, and it actually contains 64 real scalar fields. They serve as coordinates of the coset space SO8, 8 over SO8 times SO8, which is the coset space characteristic of half-maximal supergravity. The scalar potential V is built in terms of an embedding tensor, which encodes the fluxes, both metric and gauge, and it decomposes into 3 irreducible representations. The 4-index totally antisymmetric representation, the 2-index symmetric and traceless representation, and the trace. These are irreducible representations of the duality group, SO8, 8. Consistency of gauge supergravity requires that some quadratic constraints on the embedding tensor are also satisfied, and these quadratic constraints, upon a proper dictionary between embedding tensor components and fluxes, these quadratic constraints correspond to the Jacobian Bianchi identities I was mentioning in the previous slide. So equipped with the matrix M and the scalar and the embedding tensor theta, we can actually construct the scalar potential V, which is quadratic in the embedding tensor theta, and it depends on I powers of the scalar fields via the matrix M. The dictionary between the embedding tensor component and the fluxes of the higher dimensional construction depends on the type 2A or type 2B starting point, and it depends on the specific single type of OP-DP object we are introducing in our compactification. And then what we are going to do next is to consider a specific case of study, type 2B in the presence of O5, D5 sources. We will construct such a dictionary, and then we will construct the corresponding, or I will mention how to construct the corresponding scalar potential, and we will try to extremize. Let me mention, because I forgot to say this a while ago, that we are treating these objects in the smeared limit, and we are ignoring their dynamics. So let me consider this specific case of study, and let me introduce an O5 plane, which we can set in order, well, such that it fills the external three-dimensional space-time and the free cycle of the internal space. We choose this free cycle in such a way that it expands along the eta2, eta4, and eta6 directions of the internal space, but this without loss of generality. And the target space involution associated with the O5 plane is compatible with an SL4 times SL3 inside SO8, 8 covariant formulation of supergravity, of 3D supergravity. If we consider then the full acting with a full orientifold action on the type 2B fields, and in particular on those ingredients which have purely internal components, or one leg along the external space, we are able to identify the 64 scalar fields of half-maximal supergravity as the orientifold even type 2B field. These are the fields I report in the table here. The one denoted with a plus in correspondence to the full orientifold action of the two. And let me also say that acting with a proper twisted internal derivative on the type 2B field, we can also identify the surviving fluxes, the orientifold even fluxes. And in this table, I established the dictionary between those fluxes and the embedding tensor component that we are going to use to construct the scalar potential of half-maximal supergravity, of our half-maximal supergravity in 3D. And indeed, we can construct this scalar potential, but the extremization problem is very hard to solve. We have too many fluxes and too many fields. And in order to render the problem a bit more tractable, we decided to restrict, to retain only those ingredients, fields and fluxes, which are invariant under a specific SO3 symmetry inside SO8, 8. And this SO3 symmetry is embedded into SO8, 8, as you can see the top part of the slide. From the commutant of SO3 inside SO8, 8, we can infer the SO3 invariant scalar field space, which is SL2 over SO2 to the 4. This is 4 copies of the Poincaré disk, and each copy is parametrized by a complex scalar field. We end up having 4 complex scalars, R, S, T, and U. And this, well, the names are because this SO3 invariant subsector of half-maximal supergravity can actually be intended as that they type to be, well, as the analog as an n equal 2 analog of the n equal 1 well-studied STU model. Anyway, retaining now the SO3 invariant, well, requiring SO3 invariance, we can also identify the surviving SO3 invariant fluxes, which are 13 flux parameters. They are 6 metric fluxes and 7 gauge fluxes, 2 Neves-Schwarz, 8 refluxes, and 5 Ramon fluxes. And now with these ingredients, with the R, S, T, and U field, and these 13 flux parameters, we can construct the corresponding scalar potential, which is schematically reported here. And the scalar potential, this scalar potential enjoys 2 symmetries. a scaling symmetry and a shift symmetry, which actually allow to reduce the extremization procedure into a quadratic algebraic problem. Usually we fix the fluxes and we scan for the scalar field webs, but because of these two symmetries, we can actually fix the scalar field webs and then scan for the extremizing fluxes.
Mateo cambia muchísimo. Se te está viendo.
Sorry?
Matteo, please continue. Yeah.
Okay, sorry. So I mean, we can reduce the extremization process into a let's say different so instead of finding the scalar field webs that extremize the scalar potential once the fluxes are fixed, we can actually fix the scalar field webs and then scan for the fluxes which extremize the scalar potential and satisfy the quadratic constraints, which are consistency conditions that we have to ensure and that have to be satisfied. So in particular, also to establish connection with the n=1 co-calibrated G2 construction of Maxime Meline-Fotis, Farakos, and Jotringan, so 2021, we decided to search for vacua at the origin of moduli space. And we ended up completely charting the landscape of vacua. We found 15 vacua. We found Minkowski vacua and anti-de Sitter vacua, both supersymmetric and non-supersymmetric. And these vacua exhibit quite interesting properties. For instance, these vacua appear to be all perturbatively stable within half-maximal supergravity. So the spectrum of scalar fluctuations do not contain negative masses. And this may open up, let's say, this vacua may be an arena to investigate a bit more strongly coupled dead-end CFTs. And another interesting property that we observed was that most of the anti-de Sitter 3 vacua of this table here, with the only exception of vacuum 6 and vacuum 7, all have integer conformal dimensions for the would-be dual CFT2 operators. And this happens for our internal space, which is a group manifold, it has curvature, and the presence, these integer conformal dimensions also point to the existence of some polynomial shift symmetry, which was the reason, the proposed reason behind the integer valid conformal dimensions, which were observed for type 2A and computed for type 2A DGKT vacua on Ricci flat spaces. As you may have noticed, I highlighted in green vacuum 10 and vacuum 11. And this because these two vacua exhibit further interesting properties. In particular, when resorting to a more standard picture, so when expressing the scalar field webs in terms of the flux parameters, as we are used to, one can notice that these vacua actually exhibit or allow for parametric control and for parametric scale separation. As a proof of concept, if you consider the scalings of the fluxes that I report here, and as to be intended as a scaling parameter as to take large values, then you can see that the string coupling can be made very small. The volume and also the volume in string frame can be made very large, while keeping fixed the net current of O5 D5 sources. Meanwhile, and more importantly, with this scaling, we are able to make the anti-de Sitter radius very large with respect to the typical size of the internal space. These scalings also enable us, these scalings also it is quite easy to check that these scalings are compatible with having an anisotropic internal space, and this consistently with some recent results of Jotringens and Tim Brasa, which basically tell us that isotropic compactification, scale separation cannot be achieved for isotropic compactification. So let me now try to briefly summarize and then add some further comments. So group theory and algebraic geometry are two important tools to try to systematically chart the landscape of flux vacua. And in the particular case of type 2b with O5 D5 sources, we discovered the rich structure of supersymmetric and non-supersymmetric Minkowski and anti-de Sitter vacua with very interesting properties, perturbative stability within half-maximal supergravity, and for most of the anti-de Sitter vacua we found, integer valued conformal dimensions for the would-be dual CFT2 operators. We also found that there are examples of scale-separated anti-de Sitter vacua in 3D in type 2B, which also seem to have a supersymmetric cousins, as Vincent van Emmerik showed earlier this year. Of course, the stability issue has to be further investigated. As I was mentioning at the beginning, the Swampland program seemed to tell us that non-supersymmetric vacua, anti-de Sitter vacua, to be, well, are unstable. But maybe, well, and it would be very interesting to identify the possible decay channels for this vacua, or maybe to see whether the arguments put forward in the context of the weak gravity conjecture and its sharpening are a bit weaker because we are in 3 dimensions where vectors are dualized to scalars. Also, the fact that there might be supersymmetric cousins of the vacua we found suggests that the stability issue has to be further investigated. Let me also mention that the construction or the sources and the O5 plane and D5 brane we introduced are considered in the smeared limit. So what about their back reaction? No? Is it that the fundamental question is the following: is our construction a good approximation to full-fledged anti-de Sitter solution? Well, it would be interesting to study the back reaction of the sources order by order in GS. Another possible interesting future direction to explore is whether potential instabilities arise within the open string sector when including open string effects, and I will comment on this in a while. Another interesting aspect to investigate more is concerned with the higher dimensional stability. The higher dimensional stability for our non-supersymmetric anti-de Sitter vacua. It would be very nice to go for a full Kaluza-Klein, for the analysis, a full analysis of the Kaluza-Klein spectrum of this vacua, maybe exploiting exceptional field theory techniques adapted to type 2 orientifold compactifications. And this might provide some information on how to make sense of scale separation and integer deltas from a conformal field theory perspective. Another interesting thing to explore is whether what happens with for other duality frames, type 2A or type 2B with different kind, with a single type of source, but with P different from 5. So let me maybe spoil 2 answers to the questions I just posed. So when coupling to our construction extra matter multiplets capturing the effects of open string, we discovered that these extra effects, the open string effects, do not destabilize the vacua I showed you before, and in particular, they do not destabilize vacuum 10 and vacuum 11. So there are no instabilities coming from the open string sector. And moreover, it seems that there are new examples when introducing this open string effect, new examples of non-supersymmetric and scale-separated vacua appear. And finally, let me say that we went for the full charting of the RSTU landscape for all possible duality frames, which are compatible with the SO3 symmetry was mentioned before. And we ended up having 57 independent vacua, Minkowski or anti-de Sitter, and they all appear, with the only exception of vacuum 10 and vacuum 11, with moduli fields. So it was really, let's say, so vacuum 10 and vacuum 11 are really seem to be really special vacua. Anyway, the vacua, these extra vacua, the vacua of the other duality frames may serve as an arena to make precision tests of the distance conjecture, or they could be, let's say, good for Kaluza-Klein spectrometer, and indeed they satisfy the condition that it is required nowadays to go for a full analysis of the Kaluza-Klein spectrum. An extra condition on the embedding tensor that has to be satisfied. Okay, so with this I conclude, and I thank you for your attention.
All right. Thank you, Matteo. Let's thank Matteo for his very nice talk. Are there any questions from the audience? Yeah. Sav, please.
Hi, Matteo. Thank you for that nice talk. I just want to understand better the ingredients that you're using to get scale separation.
Yes.
So, am I understanding correctly? You start with a T7 on type 2B, and then you're then quotienting, you're adding orientifolds, O5 planes, D5 branes, and some fluxes, some F3 H3 fluxes. Is that the basic setup, or?
Yes, the basic setup is that the internal space is the group manifold we mentioned, and then we have H3 flux, the H3 flux, metric fluxes, the p-form fluxes, and then we add an O5 plane and possibly D5 brane, and the single type of them. Yes.
Okay. So the metric fluxes plus the H3 fluxes. Sorry. Let me pose the question differently. If I think of this as a limit of M theory, is there an underlying geometry, Ricci flat geometry, whose limit is this collection of O planes, metric fluxes, etc., or is that not the way that you were thinking about it?
We were actually, let me say that when deducing this vacua and when analyzing this interesting phenomenological property as scale separation is, we actually used a full supergravity perspective, which now in the talk I'm trying to recover from a higher dimensional perspective. But it is really to go to exploit group theory and fill the embedding tensor with proper ingredients, which then correspond to higher dimensional fluxes. And once you have the embedding tensor properly filled upon this SO3 truncation, you get a potential, you extremize the potential, and then you end up having some independent parameters which can be tuned to get these scalings.
I see.
Yes.
No, I think I understand. So basically, you consider all possible collections of fluxes from the 3D effective perspective in terms of the potential, study the extrema of the potential, and then you would associate some high dimensional picture to some extrema of that. I mean, it's all classical ingredients apart from the orientifold planes.
Yes, yes, yes.
Mhm.
And of course, the supergravity only sees the net charge of the sources from a supergravity
Yeah,
perspective.
yeah.
We are not actually we cannot see. No, we cannot say if O5 planes and D5 planes are present or absent. No, the supergravity sees the net charge of the sources, and that's it.
Yeah, I see. I see. It would be nice to be able to get a fully back reacted kind of high dimensional picture of one of
Yes,
these configurations.
yes, we are working on that. We are working. Yeah, we are working on that. Yes, yes, yes. It is. Yes, yes. It's something we are
Okay, great.
working on. Yes,
Great, thank you.
you're welcome.
All right. Are there any other questions? Matteo, I have like a very quick question.
Yes.
So the metric fluxes, I mean, your internal space has metric fluxes. Does what is the structure actually of your internal space? Is like a nil manifold, is source manifold?
Yes. Our internal space is solved manifold, and it
Solve
is a
manifold. Okay.
two-step
Okay.
solved manifold, which
Okay.
can be thought as the product of three E2 of three-dimensional E2s sharing the 7th direction. This is the structure, the internal structure.
Okay. Yeah. We can discuss about this after the last talk.
Of course.
So let's thank Matteo again.
Thank you all.